The past couple of years were full of astronomical breakthroughs in space. Photos captured phenomena nobody had ever seen before. Ambitious spacecraft revealed new secrets about the sun and the edges of the solar system. Astronomers spotted the brightest light in the universe, found new planets circling distant stars, and detected a collision between a black hole and a neutron star that warped the fabric of space-time. Yet, it doesn't stop there. The Voyager spacecraft has gone beyond our solar system and has made a terrifying new discovery in space. Want to know what lies beyond the heliopause? Stay tuned to find out. Voyager 1, one of two sibling NASA spacecraft launched 44 years ago and now the most distant human-made object in space, still works and zooms towards infinity. The spacecraft left Earth carrying a golden record, created by a committee chaired by the late Cornell professor Carl Sagan and mid-1970s technology. To send a signal to Earth, it took 22 watts, according to NASA's Jet Propulsion Laboratory. The craft has almost 70 kilobytes of computer memory and a data rate of 21 kilobits per second at the beginning of the mission. Due to the 14 billion mile distance, the communication rate has since slowed to 160 bits per second, or about half a 300 baud rate. Launched in September 1977, the Voyager 1 spacecraft flew by Jupiter in 1979 and then Saturn in late 1980. Traveling at 38,000 miles per hour, Voyager 1 crossed the heliopause in August 2012. Until recently, every spacecraft in history has made all of its measurements inside our heliosphere, the magnetic bubble inflated by our sun. But on August 25, 2012, NASA's Voyager 1 changed that. As it crossed the heliosphere's boundary, it became the first human-made object to enter and measure interstellar space. Now more than 8 years into its interstellar journey, a close listen to Voyager 1's data yields new insights into what that frontier is like. The craft has long since zipped past the solar system's edge through the heliopause, the solar system's border with interstellar space, and into the interstellar medium. The Voyager probes have detected an entirely new kind of electron burst outside the solar system. It's the first time this unique physics has been detected by a spacecraft and could allow for new breakthroughs in our understanding of the interstellar medium, or the space between the stars. The two Voyager spacecraft were launched by NASA 44 years ago to fly to the far reaches of our solar system. They have now gone even further than that, reaching interstellar space and exploring the gaps between the stars, giving us the first glimpses of what it might be like in that mysterious zone. After entering interstellar space, the spacecraft's plasma wave system detected perturbations in the gas. But in between those eruptions, caused by our own roiling sun, researchers have uncovered a steady, persistent signature produced by the tenuous near vacuum of space. The interstellar medium is like a quiet or gentle rain, said senior author James Cordes, the George Fieldstein Professor of Astronomy. In the case of a solar outburst, it's like detecting a lightning burst in a thunderstorm, and then it gets back to gentle rain. The latest discovery from the spacecraft, using data taken from Voyager 1 and 2, saw them pick up bursts of electrons like none ever detected before. They found that cosmic ray electrons are being accelerated by shock waves that originate in major eruptions on the sun and are then flung out into space. Examining data slowly sent back from more than 14 billion miles away, Stella Koch-Ocker, a Cornell doctoral student in astronomy, has uncovered the emission. It's very faint and monotone because it's in this narrow frequency bandwidth, Ocker said. We're detecting the faint, persistent hum of interstellar gas. Ocker believes there is more low-level activity in the interstellar gas than scientists had previously thought, which allows researchers to track the spatial distribution of plasma. That is, when solar flares are not protruding it. Ocker's new study, published in Nature Astronomy, reports what may be the first continuous measurement of the density of material in interstellar space. This detection offers us a new way to measure the density of interstellar space and opens up a new pathway for us to explore the structure of very nearby interstellar medium, Ocker said. When one pictures the stuff between the stars, astronomers call it the interstellar medium, a spread out soup of particles and radiation. One might imagine a calm, silent, serene environment. Well, that would be a mistake. Like the ocean, the interstellar medium is full of turbulent waves. The largest come from our galaxy's rotation. as space smears against itself and sets forth undulations tens of light years across. Smaller, though still gigantic waves rush from supernova blasts, stretching billions of miles from crest to crest. The smallest ripples are usually from our sun, as solar eruptions send shock waves through space that permeate our heliosphere's lining. The electron bursts travel ahead of the shock waves that throw them into space. The electrons travel at nearly the speed of light, accelerating along magnetic field lines. Soon after, the lower energy electrons arrive, sometimes taking days to do so. Then the shock waves themselves are detected by the spacecraft, sometimes as much as months later. The shock waves themselves come from coronal mass ejections, which are clumps of hot gas and energy thrown out of the sun at roughly 1,000,000 miles an hour. The Voyager spacecraft are now so far away that they take a year to be detected even at that speed. What we're experiencing is a certain mechanism whereby when the shockwave first contacts the interstellar magnetic field lines passing through the spacecraft, it reflects and accelerates some of the cosmic ray electrons, says Don Gernert, Professor Emeritus in Physics and Astronomy at Iowa, and the study's corresponding author. We have identified through the cosmic ray instruments these are electrons that were reflected and accelerated by interstellar shocks propagating outward from energetic solar events at the sun. That's a new mechanism, Gernert added. These crashing waves reveal clues about the density of the interstellar medium, a value that affects our understanding of the shape of our heliosphere, how stars form, and even our location in the galaxy. As these waves reverberate through space, they vibrate the electrons around them, which ring out a characteristic frequency depending on how crammed together they are. The higher the pitch of that ringing, the higher the electron density. Voyager 1's plasma wave subsystem, which includes two bunny ear antennas sticking out 30 feet behind the spacecraft, was designed to hear that ringing. Cornell research student Shami Chatterjee explained how continuous tracking of the density of interstellar space is important. We've never had a chance to evaluate it. Now we know we don't need a fortuitous event related to the sun to measure interstellar plasma, Chatterjee said. Regardless of what the sun is doing, Voyager is sending back detail. The craft is saying, here's the density I'm swimming through right now, and here it is now, and here it is now, and here it is now. Voyager is quite distant and will be doing this continuously. In November 2012, 3 months after exiting the heliosphere, Voyager 1 heard interstellar sounds for the first time. 6 months later, another whistle appeared, this time louder and even more high-pitched. The interstellar medium appeared to be getting thicker, and quickly. These momentary whistles continue at irregular intervals in Voyager's data today. They're an excellent way to study the interstellar medium density, but it does take some patience. They've only been seen about once a year, so relying on these kind of fortuitous events meant that our map of the density of interstellar space was kind of sparse, Ocker said. Ocker set out to find a running measure of interstellar medium density to fill in the gaps, one that doesn't depend on the occasional shock waves propagating out from the sun. After filtering through Voyager 1's data, looking for weak but consistent signals, she found a promising candidate. It started to pick up in mid-2017, right around the time of another missile. It's virtually a single tone, said Ocker, and over time we do hear it change, but the way the frequency moves around tells us how the density is changing. Ocker calls the new signal a plasma wave emission, and it too appeared to track the density of interstellar space. When abrupt whistles appear in the data, the tone of the emission rises and falls with them. The signal also resembles one observed in Earth's upper atmosphere, known to track with the electron density there. This is really exciting because we're able to regularly sample the density over a very long stretch of space, the longest stretch of space that we have so far, said Ocker. This provides us with the most complete map of the density and the interstellar medium as seen by Voyager. Based on the signal, electron density around Voyager 1 started rising in 2013 and reached its current levels around mid-2015, roughly a 40-fold increase in density. The spacecraft appears to be in a similar density range, with some fluctuations, through the entire dataset they analysed, which ended in early 2020. Ocker and her colleagues are currently trying to develop a physical model of how the plasma wave emission is produced that will be key to interpreting it. In the meantime, Voyager 1's plasma wave subsystem keeps sending back data farther and farther from home, where every discovery has the potential to make us reimagine our home in the cosmos. Scientists now hope to use this discovery to better understand both the shockwaves and the radiation itself. That in turn could help inform considerations when sending astronauts on long missions to the Moon or Mars, since they'll be exposed to far more cosmic rays than they would be on Earth.